Why does the Earth have layers? Well, to answer that, we need to know how we discovered them. To peer inside the Earth is much more difficult than simply drilling a really big hole and having a look. And scientists know this, because they actually tried exactly that many times, and each time failed to get anywhere near deep enough to reveal the mysteries of the Earth's interior. The best attempt to dig a big hole was the Kola Super Deep Borehole, constructed by the Soviet Union near its border with Norway, and the project took almost 20 years from 1970 to 1989 to drill to a depth of 12,262 metres, over a kilometre deeper than the Mariana Trench. But this is still less than 0.2% of the Earth's radius, and failed to get through even a third of the Earth's outermost and thinnest layer. The drilling eventually failed due to the chaos following the collapse of the Soviet Union, but this was not the reason as to why in 2 decades they drilled just 12 kilometres, and had to drill 5 separate holes due to breakdowns. The true difficulty came from managing the effects of temperature and pressure, both of which increase as you get deeper into the Earth. Within the outermost layer, the temperature increases by about 25 degrees Celsius per kilometre. So at the tip of the drill, 12 kilometres deep, the temperature was over 300 degrees Celsius, and pressure similarly increased to unmanageable levels. So the deeper they drilled, the more alien the conditions became, until they were forced to give up. So to understand why the Earth has layers, we have to be a bit smarter. Instead of us drilling to the rocks at great depths, the rocks can be moved up to us at the surface, most clearly seen at volcanoes. So to begin to have insights, we can just look at the rocks that have erupted from a volcano and uncover their mysteries. Other mechanisms that bring rocks to the surface exist too, such as kimberlite pipes that extend from the surface to up to 450 kilometres into the Earth and can bring up diamonds from the depths. Using rocks from inside the Earth, we can begin to use computers to model what we think it's like where these rocks came from. However, with this alone, we can't get much further than 5% of the Earth's radius, since rocks from a greater depth can't survive the journey to the surface. So to go further, we have to be quite a bit smarter. We can no longer look at a rock and study it. Instead, we have to use indirect methods to pull back the curtain and learn why the Earth has layers. And the main method to do this is using earthquakes and their waves to give amazing insights into the Earth's structure. When an earthquake occurs, a large amount of rock is moved, sending massive shockwaves along the surface and into the centre of the planet. Surface waves are where the crust acts like a water wave, moving up and down and permeating across the globe. Whereas the waves that head into the planet can be split into 2 groups: P waves that are faster and can move through solids and liquids, and S waves that are slower and can only move in solids. The waves that head into the planet curve upwards due to refraction, much like light bending as it travels from one substance to another. In the Earth, waves bend away from the normal despite increasing density from temperature and pressure due to a greater increase in shear and bulk moduli. The timings and locations of where those waves reach the surface can be used to calculate the properties of rocks at great depth. Sudden and dramatic changes in the earthquake wave's bending means that it has hit a new layer. For example, if an S wave just stops, then it has hit a liquid, and in the Earth this happens about 2,900 kilometers deep. And the measured P wave pattern on the other side of the planet to the earthquake means that there must be a solid layer within the liquid about 5,000 kilometers below the surface. So, what are the layers within the Earth? At the surface, there is a thin crust that we tried and failed to drill through, ranging in thickness from 10 to 50 kilometers. Below that is a solid-ish layer that is about 2,900 kilometers thick, and below that is the liquid layer that the S waves discovered, and this is about 2,200 kilometers thick. And then at the Earth's centre is a 2,400 kilometer wide solid ball. But we still don't know why the Earth has these layers, and to know why, we have to be a lot smarter. We have to look back at something that happened billions of years ago: the Earth's formation. During its formation, the Earth consumed a lot of material from a variety of sources, with a huge range of compositions and chemistries. Materials from the meteorites that collided to make Earth can generally be split into gases, rocks, or metals, and due to differing densities, these groups of materials separated out, like how an oil and water mixture will separate into distinct layers over time. So with gases being the least dense, they floated to the surface and formed an atmosphere around the planet. And the metals are the most dense, so sunk to the centre of the Earth to create a core, leaving the rocky material to sit between the core and the atmosphere, creating the mantle. But there's a problem. Differentiation wasn't perfect, since there's metal at the surface waiting to be mined, and gases in the mantle constantly being erupted at volcanoes. And it wasn't perfect due to timing, as if a metallic meteorite had hit the Earth right as differentiation stopped, it would be stuck at the surface and would never be able to sink to the core. But even if it had hit the Earth a million years earlier, the metal would have had a million years to travel nearly 3,000 kilometers from the surface to the core, at a speed of about 3 meters per year, which is about 500 times faster than the mantle moves today. So in short, differentiation of the Earth was slow and led to imperfections, but this has allowed the diverse and varied world we live in today. But we have more than just a rocky mantle and a liquid metal core. The crust simply formed as a shock-frozen layer between the hot interior of the planet and the hostile cold of the atmosphere and space. And it formed as soon as it was allowed to, as constant meteorite bombardment during Earth's formation constantly pierced and broke up any attempts to form a crust. But when formation slowed, a thin crust could form. Over time, the crust has developed and changed, but it still remains as the thin solid layer between the cold outside and warm inside of the planet. The metallic core has a much more interesting story. For most of Earth's history, we've only had a liquid metal core. Slowly, the planet released energy from the hot interior to the cold exterior, most clearly seen at volcanoes, causing the core to slowly cool down. As the metal core cooled below its freezing point, it tried to freeze. But because of physics, it's much easier to freeze onto something solid than in the middle of a liquid. So the liquid didn't freeze despite being cold enough to for hundreds of millions of years. Eventually, the liquid cooled enough for the physics to be overcome, and the first solid metal crystal formed. Quickly, the inner core grew, as the freezing liquid now had something to freeze onto, until it reached the radius where the liquid was hot enough to remain liquid. Currently, the solid inner core grows at about 1 millimeter per year, eating into the liquid outer core, and will continue to do so until there is no liquid left. And that is why the Earth has layers.